Last we left off, we were talking about those ions. Let's see. So a positive ion is called what? A cation, yes. Yeah, don't call it a cation, call it a cation, yeah. Okay. A negative ion is called, okay. So who typically forms negative ions? Electrons typically form negative ions. An anion, okay. And so, okay, but who is going to typically, on the periodic table, which group is more commonly going to have negative ions or form an anion? Nitrogen will. Who else will? Oxygen will. That's right. Fluorine, chlorine, bromine, iodine. So all of those guys belong to what group? Well, those are diatomics, but they also belong to another group as well, too. That's right, non-metals. That's what I'm looking for. So we know that non-metals typically form anions, negatively charged ions, okay? So then who's going to typically form cations? Magnesium is an example. What was that? Nope, carbon could go either way, remember? He can go either way, but he mostly will form a negative ion if he needs to, mostly. Okay, now what group are they? You're just naming a whole bunch of off. Do they belong to a certain group? What group do they belong to? So are you just saying the alkali metals are the only ones that can form ions? Are you sure? You want to put money on it? You're not sure? Anyone else want to contribute to this hearty conversation? What was that? So what group is most likely to form a cation? That's right, that is the positive ion. That's right. So which groups would form cations? Most likely. I'm giving you the evil eye right now. You can't tell. That's the evil eye. So what do we know about noble gases? They don't need anything. They're independent, right? They don't need anything you got. They're not going to give you anything, right? Because they're stable. So are they going to do anything? No. The only time they ever do anything is if they're done at gunpoint or forced to, right? Come on, guys. You gonna let the ladies represent? Does anybody want to repeat the question for him? What group are most likely to form a cation? Boy, it's a good thing that you guys aren't taking the test today, huh? Oh man. You've given me elements, right? You've already given me elements, and so far, all of the elements that you guys have given me have been correct. But what group do these elements belong to? Do you guys remember any of the groups? Somebody said there was an alkali metal, and there was the alkaline metal, and there was a transitional metal. What? Say it again. Say it louder. Say it one more time. Say it one more time. Okay, so she just told you the group. Now, what group is going to form cations. Metals. So why are metals most likely to form cations? Because they're unstable. That is definitely true. Good answer. Okay. And then also where they're located, right? They're going to try to go the smallest distance to form a noble gas, to be like a noble gas, right? So except for those ones in the middle, we know that those guys are hot messes, but you guys also know that they're metals. They're going to form cations, okay? Post-transitional metals will also form cations, okay? They can do other things, but mostly they're going to form cations, okay? Are you guys with me? Okay, what is the lanthanoids? Where are they located? Lanthanoids. What are they? Lanthanoids. They're metals, that's correct. Okay, where are they located? And no, that's a row. So down here, that's right. So those guys down here are lanthanoids, right? So they are in period 6, right? So we have groups up top, and then down here, they start off at period 6, okay? Okay, so let's talk a little bit about the periodic table, something that you guys may have not recognized. So down here, if you look down here, right? So the periodic table is organized in a certain way that we have what we call orbitals and subshells. And then of course we have our groups and our periods and everything like that. I'm going to help you guys understand this orbitals and subshell business here in a second, right? So can everybody, you guys can see the periodic table? I know you guys can. You guys in Kalinga and Fireball?
Yeah.
Yeah.
Yes.
Okay, so you see this guy down here, right? Now, what is the atomic number here? 57. Where is 56? BA, that's correct. Okay, so here's 56, right? Now you guys notice that this here drops down and then we start going over here, right? Then we come back right up here. Do you guys see that? That's right, it doesn't, right? So the reason why it does this is so that we can get the periodic table on a nice 8x11 piece of paper. Really, the periodic table is spread further, okay? I'm going to show you what it looks like. Maybe. That's right, and we'll talk about that here in a second. I didn't say that they were perfect. They're not noble gases. What are they? What are these guys down here? Let's see, hold on. Let me pull this over here real quick, because for some reason it's not showing me the width. There we go. Okay. Okay, so now this is what it really looks like. Let's see if I can shrink it to all fit. Okay, so this is what the periodic table really looks like when we have everything in place, right? So because we want to be able to see it on basically an 8x10, because that's what we normally use, we sit there and we shrink it down to that little form. So these guys, if we go up here, you click this, right? It basically brings those guys out of their area. This is just letting us know that they actually belong up in here, okay? And so that's going to be important when we're trying to keep track of electrons and where electrons are at. Okay, so the next thing that we're going to be talking about is it's a combination of electron configuration and quantum mechanics. Okay, I'm sorry, quantum theory. Okay, so quantum theory basically says that we're breaking things up into terms of principal energy level. So those principal energy levels are those periods. You know, on the sides, 1, 2, 3, 4, 5, 6, 7 going down, right? On your periodic table, that is your principal energy level. Your sub-levels, right? Those are going to be different. So what they are, they're going to be the different shapes that are going to basically form. They're going to be called what we call S. They're going to be called P. They're going to be called D, F. And then if we went beyond F, it would be G, H, I, J, K, so on and so forth. Okay. Okay, clear. And then we have what we call orbitals. Orbitals, so in an orbital can contain 2 electrons. We'll talk about this more, so I'm just giving you the facts right now, and we'll talk about the information a little bit later. Okay, and then there's also the way that it goes. And so which direction it goes, so the spin. Okay, so let me see, best way of saying this. Okay, if you look on a periodic table, each of the electrons that would make up part of an atom has what we call an address. We call it the quantum numbers. There's 4 quantum numbers. The first one is the principal energy level. The second one will be the sub level. The third one would be the orbital. And the fourth one would be the spin that it has. Okay. You guys, we're going to mainly talk about the first 3. Okay. We're not going to worry so much about the spin. Okay. You need to know it. Okay. So the principal energy level basically goes from 1 to n. So if we look at the periodic table, 1 to n. So it basically can go on forever, right? It can keep going to 8, 9, 10. So this here, these guys are the periods. They also represent the principal energy level. The sub level, as I told you, you have an S, you have a P, you have a D, and you have an F. Okay, so in your sub levels, I'm going to break this down for you on your periodic table. This here's your S. This here's your P. This right here is your D. And this down here is your F. And actually, let me kind of clarify that a little bit. S as in snake. Let me fix this. Okay, so we have the S, the P, the D, and the F. Okay, so in the S or the S subshell, it can only hold 2 electrons. There's 1, 2 rows there, right? The P subshell can hold 6 electrons. There's 1, 2, 3, 4, 5, 6. The D, it can hold 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the F, why are they labeled like that? Don't worry, we'll get to it, I promise you. Hold your pants up, okay? Okay, so the F has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, not 15. So this guy here, these 2, they're really in the D. They're located in these blocks right here. Okay, so they're just letting us know that that's a space holder, okay, for that spot. okay? So these two are really in the D. So these guys, this one and this one are really in the D. The rest of them are in the F, okay? And you'll notice that if you hit that wide button up top, let me do it again. Okay, so you'll see right here, they're really in the D, okay? Where all the other ones are in the F. So this is that F, okay? So are you with me so far? Okay. So there's, why are they labeled like that, right? So there's a couple of reasons why. Well, we have to give them some kind of label, right? They also represent what we call the orbital, or the route that the electron is going to be taking. So the S sublevel, basically, it forms a sphere. The P sublevel, it forms kind of like a barbell. The D is really complicated. I'll show you images. And the F, it's way, way complicated. So we don't really have really good images of that. And so what they've done, they tracked electrons, right, that are orbiting the atom, right? So since they attract electrons that were orbiting the atom, they were able to get the signature of how that electron goes. So we know that electrons are constantly moving, right? Because you guys know that atoms are constantly moving. Really, what's constantly moving are those electrons. They're always moving around the nucleus, kind of like the way our planet circles the Earth, right? Are we just stuck in one spot, right? If we were stuck in one spot, we would always have sun, and the other place would always be in the dark, right? But we orbit the Earth. So that's the same thing that's happening with these electrons. They orbit it, they're constantly moving. And so we're able to sit there and get a pattern of how they look, okay? And I'll show you that here in a second. Okay, so the S holds 2 electrons. The P holds how many electrons? 6. The D holds how many?
10.
And the F holds how many?
14.
Okay, so now if you look at that pattern, so we said the S holds how many? The P holds how many? 6. Okay, so we have 2, we have 6, we have 10, okay, and then we have 14. So what would you expect if there was a d orbital? What would it hold? Or did you say 18? 18 is correct. If there was an H orbital, what would you expect it to hold? 22. Okay, good job. Okay, do you guys know why? Okay, so let's talk about this, right? So now in those subshells, we have what they're called orbitals. The S orbital has 1 subshell. Let me write this down, and then I'll explain it to you after. S orbital has 1 subshell. The S subshell has 1 orbital. The P subshell has 3 orbitals. The D subshell, it has 5. The F has 7. And if we follow that pattern, the G is going to have how many? And the H? Okay, so each of these orbitals can hold 2 electrons. So what is the most that the S can hold? Okay, that's right. What is the most the P can hold? 6. What is the most that the F? Okay. Okay, so because of that, right, we're able to sit there and keep track of it. So the periodic table is organized in this fashion to kind of help us understand where these electrons are located, how they're spinning in that atom, right? And so that is the whole concept of quantum, being able to know where that location of that electron has to be and how it's spinning in that atom. Because if you do chemistry the right way, you can actually mess up a single electron at a single location, and that can cause a lot of havoc. Okay? Are you guys with me so far? Okay, so I told you about the sub-levels, you know, all of the different sub-levels. Now, all of this is also based upon energy, okay? So in terms of energy, the electron is going to occupy the space that has the least amount of energy, right? First, and then it's going to work its way up because it's lazy, just like us, right? How many of you guys wanted to take this class in the summer? Anybody was like, I really want to take chemistry this summer. I don't want to sleep in at all. I just want to work my butt off and listen to Dr. Henry yell at me the whole time. That's why you're here? Okay, that's good. That's good. Because I'm telling you, if I didn't have to work, I'd be at home sleeping, you know, until about 1 or 2 o'clock. I'd eat a little bit. I may go play basketball or something I consider fun, right? And then I'd call it a day, you know, that would be it. That would be my life, right? But I have to work. Okay. Although I do find this kind of fun, you know, sitting there talking about chemistry. And if I could go in and blowing up a couple of things using chemicals, that would be the perfect day for me, right? Do I get a, okay, wait. So there was a question. Hold on. I know you guys get excited about my conversation here, but there was a question here. What did you ask again? I get paid more because I have a PhD. I won't say I get paid a lot. You know, the way I look at it is your guys' brains are in my hands, right? Now, there are how many of you guys in this class? A lot, right? And then I have another class, their brains are in my hands, right? And then I have another class, their brains are in my hands. Well, I do consulting on the side. We'll talk about that a little bit later too, right? But mostly I teach because I don't have any time for anything else lately. So, and in terms of, if you think about the value of your brain, right? Your brain is pretty valuable, right? If I teach you guys right, you guys are going to do incredible things. If I teach you guys wrong, boy, you can cause a lot of havoc, right? And if I just like, don't teach you anything, oh, that's just a waste, right? So I have a lot of power. You guys look at it that way, right? And so you're hoping that I'm using it the right way, right? Yeah. Okay, so we're talking about energy, right? So this is all based on energy. So these levels, these principal energy levels represent states. So if we go back to the periodic table, are you guys with me? Are you sure? Peanut Gallery, are you guys with me over there? Good. So what did I just say? That was the guys over there that were talking. Peanut Gallery, right? Because peanut galleries are making those conversations on the side. What did I just say about energy levels? Energy levels. Yeah, you guys back over there in the corner. Right here, right underneath the TV. What did I say about the energy levels? So you guys remember, right? This is my class, right? I'm the center of attention. I'm the pretty one. You need to pay attention to me, okay? So keep that in mind. Okay, now, and if I have to talk over you, I'm gonna get really nasty if you haven't noticed yet, okay? So we were talking about energy levels. I do want you to respond. I want you to respond to me. If you're not talking to me, right, then we're not talking. We can talk to each other, long as we're talking to me, I'm included in that conversation. I wanna know about her hair too, right? But we can talk about that part after class. In class, we're talking about chemistry. So you should be telling me about that energy level. So which one is gonna be the highest energy level? Which one do you guys think? F, that is correct. F is gonna be the highest energy level out of the S, the P, the D, the F. But they're also separated from the lowest to the highest, right? So principal energy level. So that principal number, right? That represents the lowest energy level that we could have. That's going to be the first place the electron goes. That very first electron is going to go in the 1s, right? The second one is going to go in the 1s as well, because we know that we can have 2 electrons in the s, okay? So let me kind of explain this to you in a little more of an organized fashion rather than just throwing numbers at you. Let's say, for instance, we're talking about nitrogen. Nitrogen has how many electrons? Nitrogen has 7 electrons. Every one of those electrons have a specific address associated with it, right? So those are the quantum numbers, right? So we're also going to do what we call electron configuration, basically letting me know where all of those electrons are located in a general space, right? A general idea. We're not taking all of the quantum numbers into account. We're only going to take a few of them, okay? So I told you it always starts at the lowest energy level. So we're always going to start, in the case of nitrogen, I'm going to write it up here with the big N. Isn't that the symbol for nitrogen? Okay, so we have how many electrons? We said 7. So the first energy level is that first principal number, that 1, okay? Well, that first energy level can only have an s orbital. How many electrons can an s orbital hold? 2. So we're going to put that 2 up here as a superscript afterwards. So let me know that there are 2 electrons that are there. Okay, so I'm going to mark this off so you guys can see what I'm doing. So that's 1, 2. Now, again, we're going to nitrogen, right? We're going to get to nitrogen. So then we go to the next energy level. And that's 2. That's the second energy level. So that's 2. It starts off here. This is the s part of it. So that's 2s. And how many electrons can it be held in that s orbital? 2. And then we have 1, 2, 3, right? So this here is what orbital, what subshell again is this? It's the p subshell, right? And so we'll write, it's also in the second energy level. So we're going to write 2p. And how many electrons were left there? 1, 2, 3. So that is the electron configuration. We're basically an account, right? Every electron that it has. Are you with me? No? You want to give it another shot? Okay. So let's say we had something like fluorine, okay? So now we have fluorine. I'm going to write fluorine underneath here. So fluorine symbol is F. I'm going to use pink so I don't have to erase all the stuff that you guys have done. Maybe it shows up pink. Okay, so this is that first energy level. So we write down 1s. And how many can the s hold again? 2. Okay, so then that accounts for this guy and that guy. And then we go to the second energy level. So write down that second energy level, it's 2. And then the first one is an S. So, and then it holds how many? 1, 2. And then we have this guy over here. We keep going across. What is this energy level? What is this subshell? It's the P subshell. So we'd write 2 P and 1, 2, 3, 4, 5. Okay, so all we're doing is keeping track of every electron there is. Okay, we know where it's at, we know the energy level, and if we really wanted to, we could even break it down further. And I can tell you that if it had a hot date the last night before, That's a joke, really. Okay, so are you guys with me so far? Okay, so now I'm going to make it a little bit more challenging because we have something that we call degeneracy, right? Degeneracy basically means that it's going to mess up our little system, right? It's going to break it down a little bit. So here we have the 1s. This guy started at the 2s, and then we have the 2p, and then we would go to the 3d, right? I mean, sorry, 3s, 3p, and then this guy actually starts at the 3rd energy level. Even though it's at the 4th, it crosses that level, right? And it's kind of weird because the 4s is lower in energy than the 3d, okay? So really, we're gonna start 3d down here, okay? So, and let me explain to you why this is gonna be important. So when we get iron here, and we're going to write down the electron configuration for iron, we need to know that this guy starts at 3d, okay, and not at 4d, okay? Are you with me so far? Okay, so I'm going to erase the nitrogen, and we're going to put iron there instead. So I want you guys to work with me. I'm going to clear this out. So we're trying to get to iron. We want to account for all the electrons in iron. Okay, so where am I going to start at? Which S? 1s. Why do we start at 1s? Diego, why do we start at 1s? You don't know. Somebody tell Diego why we start at 1s. Is it because it's the 3rd energy level that we're going to start at 1s? Because it's the first one. It's the lowest energy level. We always want to start at the lowest, right? Aren't you lazy? Be honest. He's like, hell yeah, I'm lazy, right? So if you don't want to do any more energy, you're not going to do it, right? You want to try to go to the lowest energy level as possible. Okay, so we have 1s, 1s2, okay? Then, so that counts right here. Then we go to 2s2. And then 2p6, that is correct. So then that gets rid of these guys here. Okay, then 3s2. Three P, that's right, 3p. P6. 4s. 4s what? No, because S only holds how many? 2. Okay, so it's 4s2. So that's 1, 2. And then we go to 3d. Because that's the d orbital in the middle, right? So it's 3d what? 3d6. Yes, so all of the D areas are now shifted. So then this is 3D, this guy is going to be 4D, this guy is going to be 5D, this guy is going to be 6D. Now, the same thing happens with the F, down 1. So let me scroll up. So these guys, this guy's going to be the 4F, that's going to be the 5F. So see if I can move everything so that it'll adjust appropriately. Are you with me so far? Okay, so this guy is going to start off at the 4F. And then this is going to be that 5F. So when we get down to here, okay? Are you guys good so far? Yeah. Yep, you go through the same process, yeah. So then that would be the 5S, 4D, 5P. So let me move you guys down. We'll do one more, so then you guys can kind of see how messy it can get, right? Okay, so let's do something that's challenging. So we're going to do SM. What was that? You always have to start from the top, okay? So we're going to do SM. Do you guys see where SM is located? I have it, it's right here, down here, right? So it's, what is this atomic number? 62, okay? So we're gonna start. We have 1s, 1s2. Okay, so then two S, 2. Then, so then that 2P, 2P6, three S2, and then we have 3P, 3P6, so yes, 4S2, that's correct. Then it's 3D. Three D10. That's right. 4P6. Okay, 5S2. Okay, you said 4. So we had, wait. We had 5S2. And then what's after 5S2? 4D10. (4D10). Okay. And then what's after 4D10? 5P6. Six. 2S. Okay. Are you sure it's 5D10? Follow the atomic numbers there. We have to go to the 4F. That's correct. So then you go 4F, right? 4F what? 1, 2, 3, 4, 5, 6. 4F6. And then you're done. Okay, so what did I say with the perfect was? The purpose of it was again? You know where the electrons are located, right? So if you know where the electrons are located, so depending on how you submit that energy, how you put an energy wave in there, you could affect a certain electron. You could polarize a certain electron. They're located in the S subshell, right? All 6 of those electrons are located in the S the F subshell, right? Where you have electrons located in the 6s2. Yeah, yeah, so you're telling me, I just told you where every electron it is in SM. How many electrons does SM have? How many electrons does it have? Somebody say it. It has 62 electrons. If you count these superscripts, that's 2, that's 4, that's 10, right? That's 12, that's 18. Well, because you want to know, because you're not listening to anything I'm saying, right? Because, wait, listen, because you want to know where each of the electrons are located, right? The reason why you want to know where each of the electrons is located, because you can cause certain things to happen with exciting a particular electron, right? So if you have one that's in a 6 energy level, it's going to behave differently than the one that's in the 3, right? And I'm going to show you this. I'm going to prove it to you because I know you're doubting me, right? But I'm going to prove it to you. It's okay. I don't mind proving it to you because, you know, seeing is believing, okay? And so your lab is actually going to show you, okay? Are you guys with me so far? Okay, I like her. She asked a lot of why. Why? Why is the sky blue? Good job. I like that. Yes. Can you repeat that, please? Because when we get here to the 6s, it drops down. If you look at the atomic numbers, it goes 55, 56, then 57 is down here in the 4F level. It's because there's what we call degeneracy that occurs. Each time you add another shell, another subshell, you drop that number, you subtract the number. So like when we are here in the 3D, right? So it's the 4 energy level, but we added the D subshell now. So we have to subtract that one number, right? And so really what it is it's really in the, and I'll kind of explain this to you simplest way possible. So you have the 4S energy level here. You have the 3S energy level here. And let me put it on the board. Actually, there's a picture. Hold on. Because I'm saying the same thing and they're not seeing anything either. Can I erase this? Can I erase this right now? Everybody got this down, right? So let me clear it. Okay, so let me see if I can. Okay, so everything is based upon energy, right? So if you take a look at it here, here's the 4S. 4S is actually lower in energy than the 3D. And so when we have the periodic table organized, it's also based upon energy overall. So that 4S is lower than the 3D. Even though it's in the 3D level, right? You always want to put in the one that's in the lowest energy first, you know, because again, lazy. If you're going to do something, right, and you can get away with doing the minimum amount of work and get full credit for it, you're going to do the minimum amount of work and try to get full credit, right? Anybody just do extra work just to do extra work? If you do, let me know because my house is a mess and I need somebody to really come and clean it. Because if you just want to do it, I won't pay you a dime. You know, if you want to do it for free, you know, it's perfect. I'm cool with that, right? So now on that same level, the electrons are going to behave the same way. They don't want to use any energy. They want to try to get it for free if they can, right? And so you're always going to go to the lowest energy state that you can go to. And so since 4S is lower than 3D, it's going to go to the 4S first. Do you guys see that? So if we go on the periodic table again, so here, this lets us know that that's the 4th energy level, right? But I told you guys that the D starts off at 3. Right? So this here, right here is the start of the 3D. Right there, okay? So we fill up that 4S first, and then we fill up the 3D, okay? Because it's lower in energy, okay? So you're putting electrons in as in the state of the energy level, right? Lowest one first, right? Try to save and conserve energy. But that's a good question. And again, that process is called degeneracy. So we know that we have the 1s, right? We know that we have 2s, 2p. Then we have 3s, 3p, and we have 3d. We have 4s, 4p, 4d, and 4f. Then we would have 5s, 5p, 5d, 5f, and if we got to it, we would have 5g. Oops, let me see. Yep, that's right. Okay, so, and then we would have 6s, 6p, 6d, 6f, 6g, and 6h, right? Okay, so the way that the energy levels work is like this. Let's see, color. Okay, so that's all in that very first row, right? Okay, so let's see, am I doing it right? Then we have this guy is all in that second row, right? What was that? No, you're not going to be using sig figs. These are just, it's notations. You're going to be using 2, 6, you know, yes. Do you have to repeat that, please? Do you have to say how many sig figs there are? Yes. So well, not for this first exam, you don't, because we haven't gone over it officially, right? I'll tell you how many digits I want, right? Okay. So let me see if I can do this. Okay, but if you look at it, right? I see I'm not doing this right. So we have 1s, right? We have the 2 series, right? Then we have the 3. Then these guys here, right? It goes 4s. Let me shift this. We have what we call, as I said, degeneracy. So then, we go 4s, the 4d, and then we'll go 4p, and so on and so forth. I've got to figure out how to do this the right way. But in terms of the energy level, each time that we add an energy level, it's going to drop 1 spot, right? Because we don't have a 1p, do we? Do you guys see a 1p there? We only have a 1s. And then the next one, we have a p. And then the next one, we have a d. Because of that, we have to go drop 1 energy level, right? So the d is actually always going to be, let's see, I have to find the figure. It makes a lot more sense with that figure. It's got to find it for you. Let me find the Okay, so again, here at that fourth energy shell, we go 4s. This guy is going to start at 3d. The F is going to start at 4f. Okay, so always remember it's going to drop by that next level, right? So in the case of, since 6s, right, this would be 6s, this guy would be 5d, right? This guy would be 4f. So that one is going to drop by 2 in that case. So each time you get to another energy level or another subshell, it's going to drop. So if we went with G is going to start off on the, yeah, I'm saying if it's possible. The P would be, that's an H. Sorry, it got caught up in the corner. That's bad. Let me fix that for you. That was an H. Yeah, because then after that, after F, it just starts to act like normal letters. So then it'll go. No. I wouldn't say I learned chemistry. I learned chemistry. I mean, of course, there's a learning curve. Like right now, there's a learning curve, right? But it's a process. If you, I'm a strong believer. If you open your mind up to learn, you're going to learn. If you fight it, you're never going to learn. If you say I can never get it, you're never going to learn. Okay. So I have questions for you, right? So we've talked about ions. Hey, this is not social hour. You want social hour, you wait till after class. There's plenty of time for you guys to do that after this. Okay. So when we talk about those ions, how does that affect those electrons? It changes everything, right? Okay, so but before we get there, I'm going to teach you a shortcut. So do you guys like writing out all of those different ones? You don't? I thought you guys like doing extra work. Alicio, he says that you guys love doing extra work. Did you say that? Elise? He says, nope, you guys love it. And he was going around and he wanted to make sure that you guys did some extra work because he was being social, right? Okay, so let's put it in perspective. I'll show you a nice little quick way of doing it, right? And the way that we like to set it up is all based upon the noble gases, right? Because we know that the noble gases are important. Again, if I'm talking over you, me and you are going to have words. Okay? Are you guys talking about I hear you guys talking about what we're talking about right now. That's cool. I don't mind you talking about what we're talking about. But don't get behind because we have to stay in effect. We got to keep things moving. So we were talking about ions. How are the ions going to be affected? But I said I was going to show you a shortcut. You know, I may change my mind since you guys are giving me a little bit of a hard time. You guys want to work hard. Oh, you want to learn it? Oh, so I got your attention now? Okay, good. I just want to be sure. So since I got your attention, the way that we do the shortcut, we use the noble gas, right? So let's say we're going to do something like, let's do one that's down here. HO. You guys see HO down there? You guys see HO over there in Kalinga? Yeah. Okay. So the way that we would do it is we would go back to the nearest noble gas that's behind it. So HO has a number of what? 67? Okay, so we want to go to the noble gas that is lower, the nearest noble gas that is lower than 67. What would that noble gas be? Xe. Okay, so this is our noble gas. Okay, so we're going to write that element. We're looking at HO, right? Then we're going to put that noble gas, Xe. And then we just go till we get to HO. So then that would be 6s2 and then we go down to 4. Remember, we start off at 4F. 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 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, simple. Yes, if you want to write it the long way, go ahead, knock yourself out. You can write it the long way. Yes, it is the same way as writing it the long way. So the thing that we're doing now, we're using a noble gas as a core, right? So by using a noble gas as a core, it lets us know that all of those guys are accounted for, right? That's stable part of it. So if I got rid of these 13 electrons, I'd be just like that noble gas, right? And I would be stable, okay? So that's what it helps us recognize. So these guys here, these guys are called your valence electrons. You guys heard of that before, valence electrons? So your valence electrons are the electrons that are going to be involved in reaction, right? So those are the ones that we want to be involved in reaction, okay? So those are your extra, right? So these guys are kind of like that noble gas. These are your extra, okay? So you either want to sit there and add on to it so you'll be like a noble gas, or you want to take away from it so you'll be like a noble gas. Whichever one is going to be easier for you to do. Are you with me so far? Good so far? Okay, so we are talking about ions and how we would write an electron configuration for ions. Now, the way it works is, now when you're adding ions, you always add to the lowest energy state, right? So you're going to keep adding till you get to that lowest energy, right? And then eventually you have to go up because you're adding electrons, right? So that's easy. So it's just like what we did before. So anytime that you're adding electrons, it's just going to be intuitive exactly the same way. Now, taking away electrons is a little bit different. I'm going to ask you a question, and I want you to honestly think about it. Honestly, okay? So you guys know what a pervert is, right? A pervert. Okay. Let's say you guys, some of you guys have little brothers, little sisters, right? Okay. So let's say you have one little brother or little sister, right? Okay. So in that case, you're going to be really protective of your little brother or your little sister, unless you really hated them a lot. But for the most part, you're going to be really protective because your parents say, if you don't take care of them, we're coming after you, right? So you're going to be like, that's my little brother, little sister. Right? So you're going to be really, really, really tight. Okay. Now let's say instead of having one little brother or little sister, now you have 15 little brother or little sister. Your dad was a whore, right? And he sprayed his seed everywhere, and they're all little, right? Right? And so in that case, if you have 15 little brothers and little sisters, and your parents told you you have to watch them all, right? And you know there's one way across town, right? And everything like that, you're gonna be like, I can't keep an eye on all 15 of them. It's gonna be crazy, right? So which ones are you gonna be more in tune with? Which ones are you gonna look after more? The smallest ones, and they're also gonna be the ones that are gonna be closest to you, right? So you're gonna keep those closest to you, right? The ones that are older, you're like, you can lose that one, especially that bad one. Go ahead, take him, right? So now think about this. Now, if you were gonna take a kid, would you take the one that's closest to the person that's watching them, or would you take the one that's very far away from them? Why? Because there's no eyewitnesses. Would you take the one that's closest? Now, what's going to happen if you're a pervert and you try to take it from, a parent or a big sister? What is that big sister going to do to you? She's going to beat you up, right? So which one is going to take the least amount of work? The furthest one away, right? So the furthest one away is going to be easier to pluck because it's far away, okay? So in the case of the atom, which one do you think is going to be easier to pluck? The one that's closest to the nucleus or the one that's furthest away from the nucleus? The furthest away. So you're always going to pluck from the one that is furthest away. So let's say we're talking about HO plus 2, HO plus 2. That plus 2 means what? It is a cation. We know that it's a cation. That means it has a positive charge. That also means what? So we're removing electrons. How many electrons are we removing? 2. Okay, so I just told you, if we're going to take it away, where are we going to take it away from? The furthest. Now, who is the furthest? Is it 4F? It is the S. That is correct. 6 is greater than 4. So it's furthest away, right? So this would be, oops, XE for F11. And we would be taking away from the S. We'll take these 2 away. Okay? So you're always going to take away from the furthest one, or the biggest number. Okay? Are you guys with me? Okay. Okay, so let's look at lead and lead 6+. I want you guys to write the electron configuration for lead and lead 6+. So let's start off with lead. So we have PB. Okay, so then what are we going to put? Okay, so we're going to put XE. I'm going to put that in brackets. Six S2. What was it? Now follow the road. So 4F14. No, 5D10. Because remember, it can only hold 10. Chapter 11. You mean 6P2. Okay, are you guys with me? Okay, so remember this. For me, on my periodic table, what I would have done, if I was allowed to do that, I would put 4F down here to let me know that this down here starts off at the 4F, just like I had this written as 3D earlier, right? And then I know that those are going to be the only changes, the D and the F, and anything that's above that, okay? So let's go back. So the nearest noble gas, so here is PB, right? So if I go back to the nearest noble gas is XE. So that's where I got that XE from. Then I go 6S, my bad, 4F14, then back up here, because this is where it goes back up to, because it goes 71, then the 72. Then it goes 5D10, and then 6P2. You guys see it? Do you guys see that route? Okay, simple. Okay, so now we want to talk about PB 6 plus. Okay, what are we going to write for PB 6 plus? XE. Now, what does that 6 plus mean? We're going to take away 6. Okay, so which ones are we going to take away? 6S2 or 6P2? 6P2 first, okay. Got that one, okay. And what else? 6S2, and then? Okay, so then my answer should be 4F14. D8. Got it, Angel? Again, is it going to be easier to take? You're always going to take it away from the one that's easiest to take from. So you're going to take the ones that are in the outer shells first, right? So the bigger numbers, okay? So you're going to take away from the ones that are in the six first. So you're going to get rid of that one. P, the P is bigger than, say, P is further away than the S. So you're going to go with the P first, then the S, and then you have 5, because 5 is greater than 4, right? So you're going to take away from that one first. So you got 2 here, you have 2 here, so you need 2 more. So then you're just going to take those 2 from the D. Okay? Sure, we can try another one. Okay, everybody got this down before I put the next one up? Okay, so let's do uranium. Yeah, this is just finding, this is electron configuration. So I'm going to do uranium, U, and we're going to do U. U3 plus. Okay, so for uranium, this is what we're doing now. Okay, so what is the noble gas I'm going to use? Rn. So we use bracket Rn. Okay. Then I heard 7s2, and then 5f4. That is correct. Okay, so we're removing 3. Where are we taking them from? So then what am I going to be left with? 5f3, that is correct. Okay, piece of cake? Good, good. Okay, a couple of more things, and then I'm gonna let you guys take a quick break while we try to get set up for your lab, okay? Let's see. Okay. So we're talking about those electrons. The electrons are orbiting the nucleus, and this is just like an example of that. So Bohr basically had it set up like this. This is what really is what we're expecting things to look like. And so each of the different subshells have a different type of orbital, right? So the S subshell looks like this, just a sphere. The P subshell, this is one set of orbitals for the P subshell. This is the second orbital for the P subshell. This is the third orbital. So you have one on the x-axis, one on the y-axis, and one on the z-axis. This here is the D. You see how hot mess this D is, right? Now the F is even worse, okay? So usually they don't show us a picture of the F because D gets kind of crazy. So just imagine what F is gonna look like, okay? And then there's the possibility of the G. We haven't put enough electrons in to get to the G yet, but it will happen someday. We'll start finding elements that'll fall in that category, So real quick again, if you look at it, the 1s is really close to the nucleus. The 2s is going to be further away, the 3s. So it's going to get bigger. So the atom gets bigger as we go down the period, right? So an atom that only ends up in that 1s, like hydrogen, is going to be really small compared to something like francium, which is at the very end. So let me give you an example. Here's hydrogen, here's francium, right? Francium is going to be huge. It's going to have a big old butt, right? Hydrogen is going to be really tiny. It's going to have a tiny butt, okay? So as we go down the periodic table, atoms get bigger. As we go from left to right, atoms get smaller. The reason why atoms get smaller is because they have more protons that are pulling the electrons closer, okay? So as we go, again, from left to right, am I saying it right? Left, yes, left to right. As we go in this way, it's going to get smaller, right? And then as we go up, it's also going to get smaller, okay? We'll talk about the gray ones. They're not stable. They haven't figured them out. So those are man-made. They've been playing with them, but they haven't got them stable yet. So that's the reason why they're gray. Yeah, so in other words, you don't have to worry about it so much yet. You're probably not going to get one to have to write the electron configuration for, but you should be able to do it if you need to. Okay. Okay, so let's see. We have rules. One of those rules or principles is called the Pauli exclusion principle. Basically, the Pauli exclusion principle basically says that you can only have either an unoccupied orbital, you could have an orbital that has one electron, or it has two electrons. It'll never have all four electrons in one, or all six in one, right? Orbitals. So remember, the P, it has three orbitals. Basically, it has three sets of chairs, matching chairs, right? So you can sit two people in this first set, one in one direction, one in the other direction, one in one direction, one in the other direction, one in one direction, one in the other direction. Each of these represents those orbitals. That's one orbital, that's two orbitals, that's three orbitals, right? You can only have two electrons in there at most, either nothing, one, or two, okay? So that's what the Pauli exclusion principle says, okay? You're always going to go from lowest energy level to a highest energy level. Okay, so are you guys with me so far? Okay, good. So talking about your exam is going to cover up to, we're not going to include electron configuration, but everything that we covered on Monday, right? So you need to be able to sit there and tell me about ions. You need to tell me about isotopes, right? You guys need to be able to balance chemical equations. You need to tell me what macro means, micro means. You need to tell me about solutions, right? Different states. Different states. Yeah, if it's a chemical reaction, is it a physical reaction, right? Types of reactions. That's right. So, did you guys see the discussion? Everybody saw the discussion? You guys are working in groups for those discussions, right? Yes. Yes, you need to turn in it as a group. I'll set it up so you guys can turn it in, right? As a group. So one person from your group needs to turn it in. So don't get anxious. Make sure you talk to your group before you turn it in, because it's worth points, right? So you get extra points if you got them all right. You guys know what that works? The first group that gets it all right, that turns it in, gets the most points, and we break it down from there. Okay? Okay, there's something else I wanted to tell you. No, your groups, all the groups are all the groups of all the classes that I teach, right? So it may be somebody in Fireball and in Kalinga. So your group is all mixed up. Okay. So you want to reach out to them. The way that you guys reach out to them, if you guys go onto the Canvas shell, there is a symbol that looks like this. Okay, so you can't make fun of my drawing. There's a symbol that looks like this. Okay, that means group, right? It has two bodies that are there, okay? Oh, it's not showing it. Oh, sorry. Yes, you can take your test on Monday here if you want to. You can also take it online, right? So, but you need it to take it online, you need to have Proctorial install on your system. So if you go to the exam, there's an exam that says faux test. I'm going to open that up. That'll get Proctorial installed on your system. Also, there are going to be little links associated with that. I'll be putting this up tonight so that if you're having trouble, you go to YouTube to fix it, right? You click it, it'll take you to a YouTube video, and they'll tell you how to fix the problem. Okay? Follow the instructions. It works. Yes, ma'am. Okay, so don't worry, I got you. I got you. Okay, so on the exam itself, there is going to be a feature that you can actually use the calculator available there. So if you're doing it online, there's going to be an online calculator available for you to use. Okay? Any other questions? Yes. Yeah. Yeah, it'll shut everything down. It drives me crazy sometimes because I forget to unlink mine. As the instructor, does the same thing to me too. Yes. I have to fix the practice test because all of the stuff that was supposed to be put in there, it only put in 3 questions. And those were 3 freshly written questions. All of the other stuff didn't get imported when I imported it in. So I'll be fixing that tonight, and so it'll be available. So in theory, you guys have until I'm going to give you an additional day to get the test done. So, but if it were me, I would try to get it done early, right? Not wait till the last minute. So then you know what kind of pain you're in, and you can get your test corrections done.